And it's something we want to talk about here is learning to critique your current architectures. Now, I've worked for Oracle for a long time. Now, the worst time from an Oracle perspective is to find that your architecture or your application has been critiqued is in the sales cycle. Because if we come and tell you your baby's ugly, you don't buy from us. It's really simple. Alright? But that's actually, we're doing you a favor, but that's not good for my career, you know? So we have to take it to the next step. The worst time in the real world to find out that your architecture's not up for it is when you roll it out in production. Because boy, the finger pointing gets thick and fast at that point in time. How many people have found out at rollout that their architecture wasn't up for it? A lot of people looking at that. I don't want to admit it. Okay. But that's the reality of the situation. And if we go to the next one, the reality of today is there's not that many new systems being rolled out at the moment. Okay? There's not many greenfield sites. You know, the chance to create the brand new super duper application that we got everything right from the beginning. Because that's what you always set out to do, isn't it? But the reality of the situation is you've got landed with an existing architecture and it's tricky. You know there's things wrong with it. Okay, we all know our babies are ugly a bit. We all know it. But, you know, and a lot of that's historical. A lot of applications out there were written 15, 20 years ago when the technology was a completely different mix. We were doing things in a different way, like it was called client server and stuff like that, wasn't it? You know, on machines that called things like VAXes. Anyone know what a VAX is in the room? You know, and it was all kind of different, but we've kind of stuck with the application code. And it's something that I've noticed, and I'm going to put it out there for you all to start thinking about, because how many people would think they're a software specialist in the room? Who thinks they're a software expert and did computer science at school? Who thinks they're vaguely competent at what they do? We've got something, right? But the reality is when I grew up, even when Graham grew up, which was a little bit before then, you know, the reality of the situation was hardware was hard because we couldn't change it, you know, and it was impractical. We couldn't. So we wrote and worked in software because it was sort of soft and malleable, and you could change it. What actually has happened today is people say, "Oh, we can't change our code, but I'll flip the hardware." Is that the new reality? So has software become hardware? Or has hardware become software? I want you to think about it. Just remember what you went and did at school. We learned how to be software engineers. We sort of disempowered ourselves along the way. You know, let's just flip the hardware. It's easier. But we're not doing what we claim to be good at. Which is really a bit sad, really. I don't know. I find it very unrewarding just to live by Moore's law. It's kind of boring. You know, every 18 months you're going to get more. It's kind of tedious. So, you know, the reality is there's very few new applications. You know, the thing that I find quite ironic, people think it's lower risk to run the old code. And bearing in mind we're going through a lot of computer changes with everything suddenly being in memory rather than being on the end of a disk. CPU speeds are getting faster. Memory, I/O speeds are getting cheaper and faster all the time. There's physical changes going on. Maybe not changing your software is actually the high-risk route. Very difficult to sell. And whilst workloads and everything else, everyone tries to make an old VAX-era workload scale more and more. Not so good. So you can see, we're at a sort of crossroads. There's a lot of things happening in the computers and the hardware, and perhaps our software architectures aren't keeping up. So really, what stops us evolving? There's the technical challenges aspect of it, which is where we earn a living, assessing what's wrong and fixing the right things. But as my career as a performance engineer has developed, I realized it's not just good enough to be smart and to figure out the solution. You've got to get somebody off their butt to go and make it happen. Okay? And I found this massive amount of inertia to actually create change. Graham, is this the story of our life?
Yeah, it's very difficult to get people to change unless they're on the brink of a complete and utter disaster. I think.
And we also find when people are having complete disasters, we get to say, we'd like you to come and fix it, but we won't let you change anything. Well, because you might break it.
The chance of being able to fix it without changing anything is pretty slim.
So we've got a broken system, but we don't want you to change something and make it an unbroken system because we're frightened you might break it. How many people live under that fear? So we're bonding well here today. It's the end of the show. Work for it. Okay. The reality is, a lot of the challenges we face are human and political. Learning to critique the application. If you start critiquing your own application, who are you going to upset? Well, very often the guys that designed it. Is that your boss? Is that your boss's boss? Is it your boss's boss's boss? If it was a 15-year-old system and you figure out how careers work, you're going to offend somebody. Well, I know, I do it all the time. I'm not really worried about it. I offend people all the time. It's what I'm paid for. But that's the way it works. The reality is that, are you going to create hell? Suddenly you've got a vendor managing things and you're saying something's broken. Oh, then the corporate politics get really stirred up. And then you have to start justifying how much payback is it going to be and how much is it going to cost to redevelop. And of course, you know how good at estimating those sort of things we are. And will they pay for them? Or do we actually need to recode as a matter of survival to get through the next Thanksgiving or the next surge or the next electoral process and all those sort of things, or the next Olympics or whatever's going to take place? So we recognize it's both technically difficult, but it's humanly difficult. Okay? And one thing we really need to do as real-world performance engineers is polish our act in being able to express why something is broken without getting emotional and getting it all down to numbers and recognizing the stuff. And that's what we're trying to sort of help you get along on that sort of stuff, because it's difficult.
Numbers and demos.
Have you noticed we did a few more demos this year than we've ever done? This is the reason, because you can now send those demos to the people that need to know, and this is really important. So let's deal with the OLTP side of the fence. We're going to deal with them first. Learning to critique this sort of stuff. Very often people are going in 10,000 transactions, saying they need to go to 100,000. Their data sets are going to terabytes to petabytes. Okay? They're suddenly wanting batch jobs that were running in hours to run in minutes and seconds. Okay? The game is changing. Recognizing a bad architecture. Missed batch windows. How many people miss batch windows every night? How many people have requested to rewrite it? How many people have done it? Good. You won the argument. It's difficult. Okay. How many people miss their batch windows and blame somebody else? Alright, okay. Response time. Unpredictable response time. The one we tend to see is that hardware fully utilized, but very inefficiently fully utilized. Or likewise, software that isn't able to drive the hardware in the manner it was designed to be used. How many people have experienced serialization, where one CPU does all the work and you've got 19 doing nothing? Classic case. So it's all about being able to articulate this. It's a really important topic. So let's look at the OLTP side of things. Graham, perhaps you'd like to tell us the biggest issue we see on LTP systems that hit our desks for badly architected.
Right, and over the last couple of years, without any doubt whatsoever, it's connection management. It's having systems that are running way too many connections to the database. And our line on this is that the number of connections that you need to the database is the number of connections that allow you to fully utilize your hardware platform. Right. You'll notice that in that statement, there is nothing there about the number of users. And what we see in almost every case is that people try to scale the number of connections to the database to the number of users they're trying to support. It's one of these hangovers from the client server that Andrew was talking about. So we're going to have a little demo of that now. So we've got an OLTP transaction, a screen. Those of you who've been in others of these sessions will recognise this screen. We're running maybe a couple of thousand transactions a second. We have a response time of 2 milliseconds for each of our users, and the load on the machine is very, very low. Can we look at what the CPU load is? Yeah, so it's of the order of 1 or 2% that we're seeing. So we're running connection pools here. We're running connection pools that have an initial pool size of 3 and a maximum pool size of 64. Right, so dynamic connection pools. How many of you have middle tiers that have dynamic connection pools to the database? Okay. So despite we started off with the initial number of sessions as 96, we've only ever been running this amount of load on the system. One thing you can see is that if you look over on the right-hand side, is that we've actually got 1,400 connections. Well, why is that? It's because the way connection pools grow is, oh, I can't get a session, I'll go and create a new one then. And because we've allowed them to dynamically increase, it's increased very dramatically. Right? From 96 up to 1,400, despite the fact there's almost no load on the system. So, well, let's start cranking up some load. Currently we have 9,600 Java threads, which are each executing a transaction every 10 seconds. Yeah. So let's double that, so it's every 5 seconds. And we'll see what happens to our statistics here. Right. We'd expect to see the throughput increase in line with our reduction in think time, and we'd expect the CPU load and maybe even the average active sessions to go up. Right, we're seeing throughput go up and then flatten off with our doubling. Okay, so that's made a bit of an increase in throughput. We've doubled the throughput, so let's double it again. I mean, at this stage, and we were saying, wow, well, so far so good. We doubled the transaction rate, and everything scaled really nicely. That's pretty good. That's one down.
This is what we call the euphoria phase.
Yeah, that's right.
This is the sort of congratulations.
Maybe a couple of months after first deployment.
My baby's beautiful at scale. All the way up to 10% CPU utilization.
Right.
I've just proven linear scalability.
Linear scaling, right.
Super linear. Okay, so what are we at now? 5,000? So we've doubled it again to 2,500. So here again, it's all looking pretty good. CPU utilization on the box is what? Can we have a look at?
About 20%.
About 20%. So hey, high fives all round again, right? We've scaled up as far as 20% utilization of this box. So let's double it again.
Who runs their boxes at 20% utilization and then explains it to their boss that this is good, by the way? Quite.
Right. Okay, so now we're seeing a bit more of a ramp up. Because we're doubling each time, so getting progressively more of these. And so far our connection pool stayed pretty stable at 1400, which is good. Our throughput's doubled again. Okay. 1200, we're now at 40% utilization. Okay, now this is, we're doing, maybe around 10,000 transactions a second. So it's going pretty well. We've got a really scalable system here. Okay, let's go for it again.
Double it up.
Yeah, let's go.
How many people size their systems by the average transaction rate? Okay, a lot of people who do size it by the average transaction rate, they're still living happy at the moment. However, what do we know about what goes on with real transactional systems? It's like the wind speed on Golden Gate Bridge. It's up and down and up and down. It doesn't stay steady, does it?
What just happened there? Oops. Right. So previously, our transaction had been humming along quite nicely, just using a little bit of CPU, no real wait events there. What are those wait events, Karen?
Yes, investigation.
Right, so suddenly, as we went to transaction time of 600 milliseconds, we started seeing a whole bunch of contention events. And if you look at the number of connections that we now have to the database, because there was a little bit of a slowdown because of those connection events, now we've gone up to 2,000 connections in the database. Our connection pools are now fully utilized. Right. So at this stage, well, what are the apps tier guys saying? Bob, would you like to, instead of being a DBA today, how about being an apps tier guy?
Well, I got fired as my job as a DBA after the last two sessions, so... So I think I'll take a different approach, and maybe this time what we should do is add more users. Or add more connections.
I could have sworn I heard you say that somewhere before, Bob. Right.
Well, that was a different job.
Right.
Well, yeah, I can see Bob's point of view. If he's queuing in the middle tier, the middle tier is being held back, so we better throw more load to the database. Seemed obvious to me.
Well, I mean, we could throw more load to the database. Well, maybe we'll do it by just dropping the think time a little bit more at this stage and see what happens. When we reduce the think time to what are we at? Well, we could just throw a curveball in there and maybe do a checkpoint. See what that does to our system. Because at present we're at around 60% plus utilization on this server.
Oh, CPU raised.
We're pretty much on the edge now. So anything that we do that's going to disturb the operation of the system, like kicking in a checkpoint, is likely to cause some response time issues on the system. Let's see what happens on this. It tends to be when the checkpoint completes that we see the big spike on this one.
So you can see we've got a system here, literally on the ragged edge. Usually associated with a spike in the CPU. Remember, we've got a very busy system, there's about 60% utilization, and then the database writer kicks in and does the checkpoint. You suddenly lose 1/12 of your CPU. Well, the workload level went away. So that has to be divided against 11 CPUs. You can see we just create a spike. This is reflected in slower response times. Remember what we talked about on Monday? The application server, because it's a loosely coupled system, has an even bigger queue, and it backs up all the way to the screen, so you can see that spike. Okay, so we're putting this on the ragged edge.
So should we make it a bit more ragged?
Let's make it even more ragged. Now, we have simulated in the last 5-10 minutes what can happen in 2 seconds. Okay, well, you've seen it in slow motion, in majorly controlled manner. We're kind of lucky, and by the way, if you try and do this at home, you'll spend 2 weeks trying to learn how to knock systems over. Because we knock the system over a long time, many times before we learn how to bring the load on gradually, and be able to take it to the limit and knock it over predictably.
Well, the other way of thinking of this, I mean, this can happen, this ramp-up that we've been doing over the last 5 minutes, can happen over a few seconds, a couple of minutes in your production system. It can also happen over a couple of years if your load is gradually building up. And, oh, well, the system's never had a problem. Why do we need to change anything? There's not been any problems on this.
But have you noticed we've very reduced the think time in the transactions and increased the submission rate of transaction rate, very small, I think about 10%, but the CPU utilization went up disproportionately to the workload. Now, what I want to say about this is the more reactionary comment was saying we now have a non-scalable system, and it'd be right to a certain extent. And it's the architecture of the system that's let us down. Now, we usually find that we have to now argue for 6 weeks as to what has gone wrong. It's very often, it's factionalism. You see the application tier, people say, I want more connections. The database people say, I need less connections. And nobody can agree with each other.
Yeah, and I think 6 weeks is a really conservative estimate.
Sometimes 6 years. Okay, so you can see we've rendered the system on the point of unstable. You can even see that the instrumentation is not keeping up. Okay, it's failing to record the right values because it can't even get predictable instrumentation. How many people have loaded a system so hard the keyboard doesn't work? Okay, anyone have to do the walk of shame? You know, go down to the data center or go to the machine and pull the plug out. Machine running 99% in user space, keyboard not work, can't even type the reboot instructions. Pull the plug out. It's a really career-limiting move in certain systems to do that. It is the walk of shame.
Yeah, and it's obviously a negative. If we look at the response time that we've got there, it's all in the database. So this database doesn't scale. I mean, that's obviously the problem here. So, you know, maybe we need to move to a more scalable database. So, you know, this is looking like it's definitely, you know, all the times in the database.
So usually we get transfer connections, we over-connect, or we do something like that. Now, the discussion can usually be decided by strength of personality in the room as to what happens next. You either increase the number of connections, or you reduce it in the size of the pool. Now, I think we're going to halve the size of the pool in this case, because we didn't want you sitting around waiting for us to start 4,000 connections. That wasn't very spontaneous. So we're going to actually go down to 1,000 at this point in time. We hooked over? Okay, so we're hooking over to 1,000, and you'll see a little spike, and then we'll come back. Now, what I want you to do is take a look and see what happens. We've halved the size of the connection pool. Well, there's your dip.
So our transaction rate, we'll try and keep that in mind as well. So we were running at about 20,000 transactions a second when we were stable with 2,000 sessions. So let's see what happens when we drop it down to 1,000.
Basically nothing. The only thing you can pick up is perhaps that little bit of spikes of blue that we're spending a little bit more time now queuing in the application server than we were spending in the database when we were thrashing the hell out of each other in the database. Okay? So the game changed. Now, at this point, you really have to manage the politics. Because the app server people are going to say, well, I told you it was a waste of time. Okay? However, if you'd started off with 1,000 connections in the pool and gone to 2,000, would things have got any better? Okay, so Third day in a row.
Yeah, wrong again.
Okay. So really, we have to get back to something that Graham said earlier. People were associating the number of connections associated with the number of end users out there. On our web-based application, you theoretically have infinite number of users out there. And not all of them are nice guys. Some of them may be trying to take you out. Okay? So we need to protect our architecture from things like denial of service attacks, simulated users, and all that sort of thing you may get through. Okay? And of course it comes back to doing that first term computer science class. How many people learned in computer science when you ran 2 jobs simultaneously, it always took longer than when you ran one after the other? When we did time slicing? Well, we're just playing the same game, it's just being played out at a much bigger scale.
The other thing that you can see, when we drop from 2,000 connections to 1,000 connections, the size of those blocks in the average active sessions are actually reduced. Right? Now, it shouldn't be that surprising that by reducing the number of sessions, we're reducing the amount of contention, right? Because the things that contend are sessions. So, if we want to reduce that contention more, shouldn't we be reducing the number of sessions more? Right? Because if we're reducing the things that are causing the contention, we're going to go faster. We're going to have less contention.
So if we actually go and have, in this case, we reduce the pool size down to 96, which is a closer number to the number of actual physical cores or CPUs on the machine, which is 12, suddenly we're not doing that computer science class, and we're not thrashing and fighting to time slice, we're actually running SQL statements. Suddenly you can see the CPU utilization on the system has dropped, the workload coming on the machine is exactly the same, the transaction rate is much steadier. Where did all those wait events go to? They disappeared.
Yeah, so how many of you would have looked to reduce the number of connections to take out your TX contention on your system?
How many people would have gone to Google and said, oh, I better build a bigger number of integers in my table or in
Buffer busy ones, how do we get rid of those? Well, obvious, isn't it?
So you can see the root cause of a lot of this stuff is just not let it happen. Let the processes run and do their stuff and not fight for the resources. Okay, so we now have a system that we can live with. Perhaps we want to crank it up a little harder. We're at 450 now? 450.
Yeah, go to 4. Now, when this was at 550, we saw how volatile it was. Right? So any little perturbation of the load caused real problems, and we got big spikes. So now we've dropped the think time very much more significantly than our last drop of the think time. And look what happens to this system now. We wouldn't have been able to do this with 2,000 connections. We would have been doing the watershed.
Okay, and you can see what the middle tier, which is in the area in blue, which is the time spent waiting for the connection pool to be available. The application is coded to queue in the middle tier, not in the database machine's operating system. It's a lot more safe way to do your queuing, a lot more predictable, and you can see we've even pushed the transaction rate a little higher, so we've gone away from doing that. This, I cannot tell you the correlation that we have in terms of escalations that come into my team between high connections and unpredictable behavior. How many people have had race conditions where they've suddenly had Oracle background processes spit out trace files that are unintelligible, and then you send them to support and they say, this can't possibly happen? How many people have experienced that? It's physically impossible for this to happen. Well, you've got to think about, if you get into those race conditions, things like Oracle background processes can't physically get scheduled properly. They start missing timing windows. they start doing strange things. How many people have had node evictions for no apparent reason? Because the LMS process was fighting to get scheduled. And they said, oh, you're out of here, son. You're not responding fast enough because I overloaded you. Okay? So you can see very quickly, without someone taking the heads-up view of this, and it gets us into the next topic, we need to be able to control these systems. And it's something that needs to come probably from the top down in terms of the architecture of the system. We need to control it. Okay? Once you've lost control of these systems, it's controlling you, not you controlling it. How many people have lost weekends, evenings, holidays, Christmas, Thanksgiving, having the system controlling them? None of you doing this yet to me again.
And the only thing that we changed on this system, we changed the load, gradually applied more load, and changed the transactions. The only thing that we changed was we stopped having dynamic connection rules. We had a fixed number of connections that was appropriate for the hardware we were running on. Right? That's all we did. Nothing else.
So Graham, as my new job as application server developer manager, what should I set my min and max connection for?
Well, a good start is setting them to the same, right? So that means you're not getting the dynamic connections. And then set the total across all of your app servers to be something. A good rule of thumb is less than 10 times your number of CPUs for the entire system, right? Your full set of foreground connections to the database.
And that's a good guideline. And the reasons most people break it and don't stick to that rule is because they have all the defects we defined yesterday. How many people were here yesterday? How many spent a lot of time going, I got one of those, connection leaking, cursor leaking, block leaking, all that sort of stuff. That's the usual reason we see people having massive connection pools. It's application defects that break the rules. However, remember what I said earlier, getting it right involves running across organization. There's politics involved. Calling your development team's baby ugly doesn't make you popular, even if you're right. Okay, so try and take the emotion out of it. Show the processes that are leaking connections, cursors, locks, gather the trace in the debug, help them fix it, rather than get too confrontational about it. Okay. So in terms of getting back in control, the DBA, we noticed when we got into the race condition, the monitoring tools couldn't keep up. How many times do you find EM can't keep up? It just sort of goes... literally does nothing. So you need to be able to query the system. If you can't get anything back from the keyboard, how do you get a trace file out? Impossible. And debug issues. And so it comes down to resource management. And some people talk about resource management, thinking it's like some sort of turbocharging. I can make everything go fast on my machine because I've applied resource management. It's like, it doesn't work that way. All resource management does is stop one thing so another thing can run properly. And you set policy on resource management in order to the things that are most important to run. One of the first things you want to leave is some CPU lying around so you can get trace files out. If you can't get the trace file, you're letting the system take you for a ride rather than you take it for a ride. So one of the most simple methods we're going to show you how to control your system is anyone played with instance caging? Alright? One of the things we can do is just dial up the number of CPUs and leave some idle CPUs in the instance cage. So we're just going to apply the resource manager and you'll see a little bit of a spike. I'm not saying this is without overhead. You'll see a bump in the transaction rate. And what we'll see is that we carry on. And we start seeing some wait events in the database. Because the resource manager is now starting to stop processes from running. Okay? I think the first you'll see what the time quantum on it, maybe not showing up. But let's make it more proactive. Do you want to dial up the resource manager a little harder? And this is what the DBAs and people like that will want to do. You're going to want to dial up and dial down the amount of resources that you allocate to a database at choice. So you can slow it down and speed it up.
And what we're doing here is essentially telling the database how many CPUs it's got to work with. That's all we're doing, just changing the number of CPUs specified for the instance caging.
Yeah. And we're definitely slowing the transaction rate. And we're certainly increasing the response time, but we're in control. Okay. Now, if you're running two databases on the same machine, you're going to definitely want to apply control because we don't want the antisocial database trampling all over another database, taking stealing resources from him. So this ability to dial up and dial down becomes an important part of command and control, taking control of the system. Okay. Now, it's kind of ironic with Oracle databases, people never tended to invoke resource management until they got burned. And the reason, though, many of the times is we never got the need because we were running on such slow storage that every time something ran a query, it ran into slow storage and it went to sleep for 5 milliseconds. So who cared? Remember what's happening in the industry. The CPUs are getting busier because the IOs are taking less time and less time and less time. You're going to find you're getting CPUs busier. And if they're all getting busy, they're going to eat up the machine before you know what's happening. Getting in control is fundamental. You can see we can dial up and dial down at will. Okay, so that's OLTP. In terms of the architecture stuff. Now, data warehouse. How many people are data warehouse people in the room? How many people are reformed OLTP people turned into data warehouse people? Or unreformed people?
I'm not sure reformed is the right word.
Because we found that people who build data warehouses like they build OLTP systems struggle. Who would agree with that? Good. There's a consensus building. This is good. All right, so we're going to build the data warehouse. It's based on a retail schema, very simple 5-table model. And you can see the most important one is the transaction. That's you buying something. And then you have a whole number of line items. And each has a relationship either with the product, or the location, and how you paid for it. Okay. We're going to load up about 1 terabyte of data. In fact, we've loaded 1 terabyte of data. We're just short of 8 billion rows. And in terms of size, we've compressed it down and made life a little. We brought it down to a 64 gigabyte problem by applying a lot of compression. We got about 12 to 1 compression on the whole thing. So the challenge that we actually see is on the data warehouse is not only the queries, but we also see a problem on that nightly ETL, loading 1 million rows or whatever it is they're at. Who has problems making their batch windows overnight? Who wants to admit it? Okay, so we're going to set you a little bit of a challenge. So in that nightly loading process, how many people are using direct path loads? Good start. Who's using external tables? Even better start. Okay, who's compressing both the source and the data when it gets loaded? No compression? You're going to need to compress it. It could be terabytes. Okay? How many people are using partition exchange operations? Good. It's all good stuff. How many people have figured out incremental statistics? Okay. Let's give you an example of what could be done with a nightly load. Now, we have the data loaded on our Exadata system. The initial terabyte of data is loaded. And we got that in 600 seconds. And we created the initial statistics in 190 seconds. Okay? That was the initial population. Now, what we want to do is show you the system. Can we get back to the machine, possibly? Okay. So you see the time we spent building it. Now, you'll notice we've got 2 big graphs down the bottom. That's the CPU utilization on the database nodes. And on the right, we've got the I/O. Okay, so what I'd like to do is just scan the data to start with. Just straight off disk, just scan the data. I'm going to change the response time. Okay, so let's have a look at, we just scan the data, just so you know what's going on. So you can see we've got a little bit of CPU on the left, but we do a lot of green. We're doing I/O from disk. Okay, very quickly, and we got up to a decent rate of I/O. Next thing I'm going to do is we're going to enable the flash cache memory, and then we'll scan again, and then you'll notice some orange taking place, as well as the green, as we write back into flash memory what we just pulled off disk. So the cumulative I/O is almost twice, because we're writing away everything we read. And then the last one we're going to do is we're going to reread them all over again. And what you'll notice is that we're actually doing stuff from the red color as well as from disk. So we get the combined bandwidth of both of them to run the query. So the machine is up and running. So what we're going to do is do the daily load. And we're going to load up 250 million rows in front of you. Now, how many people do 250 million rows a night? There must be somebody in the room. 250 million rows. So we're going to put 250 million rows. This is actually was sized off about the number of sort of supermarket transactions that take place in the western states of the United States. So we started to load it. You'll notice we're only using one node of the system, the big blue that's got CPU bound. And here we're making life deliberately hard for ourselves. We're loading from compressed data. We're loading it in a compressed format. And the thing to notice there about it, and perhaps Graham would like to comment about it, the fact that it is CPU bound.
Right, yeah, because Andrew was saying that we're using compression both on the data that we're feeding in and the data we're storing in the database, and we're also using partitioning in the database. Both of those